Alright, so in this video we're going to talk about a reaction of carboxylic acids when they react with an alcohol in the presence of an acid catalyst. So you actually have two acids here, but this H3O plus, usually added in the form of HCl, because when you add HCl to water you get H3O plus. So whatever acid you add, it gives you H3O plus. So you have your carboxylic acid, your alcohol, your acid catalyst, and it makes an ester. This was discovered by a chemist by the name of Fischer, hence the name Fischer esterification, because you're making an ester. All right. So what we'll do is we'll go through the mechanism of this. It's actually really quite similar to mechanisms that you've seen previously. It shares some similarities to when we reacted alcohols with carbonyl groups, with aldehydes and ketones to form acetals, that sort of thing. So let's see what we can do. Now this mechanism is outlined in the book in chapter 16 on page 645, but well, frankly it doesn't do a very good job, so I'm going to try and make it a little bit clearer for everybody. Now all these steps are reversible, as you've seen before. So we're going to start from benzoic acid and make, in this case, ethyl benzoate. All right. So let's move on to another page and actually draw out what we'll start with. Now we're going to go in blue here because, well, I don't know why, but we have blue. If you don't like blue, well, get over it. Alright, okay, so here's our benzoic acid. And let's draw our H3O plus as well. If you remember from when we first saw alcohols reacting with aldehydes and ketones to make acetals, we saw that was in the presence of an acid catalyst because the alcohol wasn't strong enough to react with the carbonyl, and it's kind of the same here. So we have two oxygens here, one of which is going to react with the acid. Now, if you remember from what you saw previously in the reactions of amides, if this was an NH2 here, you saw that you could funnel electrons in here and up onto this oxygen, making the oxygen more nucleophilic than the nitrogen. And so for this guy, it's kind of similar. You have an electron pair here that can funnel electrons into here, kick them up onto here, meaning that out of these two oxygens, this one's the more nucleophilic. So that's the one that we're going to start with. And that's the one that's going to pick up the hydrogen from the acid. So let's just show that happening. Alright. Now you remember I said all these steps were reversible, so we're going to show that. We have a funky color change of our molecule here. So all we have at this point is our protonated carboxylic acid. And so what we've made at this point is a carbonyl carbon. Because it's got a protonated oxygen next to it, it's even less stable than it was before, so it's much more susceptible to being attacked by a nucleophile. It's much more electrophilic. So let's draw out our alcohol. Our alcohol looks like this. It's 2-carbon alcohol. Alright, and that is, well, where is that going to attack? Well, every time you have a nucleophile, it always attacks the same place, and it's going to be the carbonyl group. So let's funnel those electrons up onto the oxygen. Alright. Here comes our next step, so let's draw that out. So here we go. Let's see. Now I've made an OH group here. I still have my OH group from over on the right hand side there, but now I've added in this guy. There's my ethyl group. Here's my hydrogen. Now you'll notice from there's a similarity here to what we've seen before. Plus charge, there's got to be a plus charge here somewhere. And of course that plus charge is on this oxygen. Alright? Okay, now let's see if we can figure something out here. We know that our final product looks like this. So we also know that this group is the one we want to keep on. And we could go back the other way, but that's not really going to get us anywhere. So what we need to be saying is, well, if that's my ester product, well, I have to lose one of these two. So how are we going to do that? How are you going to lose one of those two groups? Well, you're not going to do it in one single step, but let's see what we can do. This step that we have here has the initials PT. Now, who knows what PT stands for? Because I'm taking something and moving it somewhere else. This is a proton transfer. So I'm transferring the proton that was here. It's going to go somewhere else. In fact, I'm going to show it being attacked by this oxygen. So here we go. It's kind of a long curly arrow here, but you know, I like my curly arrows. So that goes around and grabs that hydrogen, breaks that bond and puts those electrons onto the oxygen. So what we get here, if I draw out the ring again, it'll look something like this. Here's my ring. Alright, here's my OH from before that I didn't do anything to. Here's my OH, which is now an OH2 plus. And then here is this guy. Alright. Okay. So we're a little bit closer to letting this guy be kicked out, and we're actually almost close to being done with the mechanism. So we are very close. This isn't that long of a mechanism. Like I said, you're almost there. We need to find some way to kick this group out. And from what we've seen before in previous mechanisms, something helps it out. A pair of electrons goes along or goes in, forms a double bond and kicks that guy out. Now we have two possibilities here. Down here or up here, both kicking that out. And one of these, only one of these works. All right? Let me show you which is the one that actually works. If we put these electrons down into here and kick out that leaving group, I'm hoping you guys can see why this works and doing it the other way would not. If I draw out the product again, or the next intermediate I should say. Here's my doubly bonded oxygen. It's still got a hydrogen on it. And here is the rest of my ester there. And there's a plus charge here. Now I just generated some water just a minute ago. Alright. So let's draw that here. And bear in mind we said this was an acid catalyzed process, so we have to regenerate H3O+. If we'd gone the other way, I'm not going to actually draw this arrow out, but if I'd gone up here, kicked those electrons here and kicked that out, I would have had an ethyl group coming off this oxygen. And the reason why that doesn't work and this does is that this water can grab this hydrogen and give the oxygen two bonds back. If there was an ethyl group here, that wouldn't happen. That wouldn't be allowed to happen. So whenever we have a fischer esterification like this and you've protonated one of the alcohols, it's always the other one that gives its own electrons to form a double bond and kick out the leaving group. So what we have here then is this goes onto here. Alright, showing our arrows to what is now going to be our final product. So here we go, here's that. Here is our carbonyl. There is our finished ester, and we have also generated our H3O+. So that is the mechanism for a fischer esterification. As you can see, it's not really all that involved. All right. So if I was to ask you, okay, here is an acid. Here is some methanol. And if I were to say HCl, I want you to understand that HCl means it's just H3O+, it's just an acid. could you draw out the product? Well, the simple idea about a fischer esterification is that all you're doing is essentially overall replacing this by this. And that bit comes from the alcohol, this guy here. So if we just do the same thing, if we're going to say, well, we're going to replace this with this, then you can figure out what your product's going to be. There's my carbonyl, that's essentially the same. I've lost my OH group, essentially, and then I've made this. Alright, I don't want to see anything funky like this, and I will take off serious points if I see something bizarre like this. Because not only is that a Texas carbon, that's a, well, whatever the term is for an oxygen that is all messed up. That is not going to be something I want to see. So bollocks to that. Alright. The oxygen is what forms the bond there. So therefore this is right. Ding, ding, ding. Correct. Well, it's not really a correct sign, but whatever. So that is the fischer esterification in a nutshell. Alright. Not really that complex. So there you go. These pretzels are making me thirsty.